We'll continue here in chapter 35 on refraction of light as opposed to reflection, which was the last chapter. In this module here, 35.2, we're going to talk about Brewster's angle and the dispersion of light. It turns out that as light is incident upon something like water or glass or something that's transparent, of course, part of that, if I draw a perpendicular here, and here's the light coming in, part of that is refracted. It means it's bent back toward the normal. If this is air here and this is, say, glass. So part will be bent back this way. The other part will be reflected, so it'll go off in this direction here. And if this is theta 1, then of course this will be theta 2. I'm sorry, this will be theta 1 also. This angle down here will be theta 2. And it turns out that for as the light is reflected from such a surface, the light that comes in, if it's not polarized, will be partially polarized in the outgoing wave. Now, a complete polarization occurs for this reflected light at one particular angle, where the index of refraction is equal to the tangent of theta p, which is theta for polarization. And therefore we can solve for theta p, called the Brewster angle, and the tangent of that angle is n, or if we want to, n2 over n1, which is the ratio of the two indices of refraction. And we're taking air and glass, so it would just be this other one here. This would be n for the glass, and this would be n1 for air, or 1. So we're thinking of this as n here, or n2, down here in this glass. And at this angle, this incident light is totally polarized. And polarization, as you know, comes from the electric field, as we discussed in a previous section. As light is moving along, it's an oscillation in the electric field in a particular direction. The magnetic field would go in and out of the paper at this point, perpendicular to this, and the wave would travel in this direction. Polarized light is where the electric field is all plane polarized. It means that all the electric field is going up and down. Normally, if I look at this on end, some of the electric field will be going up and down, some at this angle, some at this angle. It's going to be at all different angles because the light's going to be totally mixed. It's only when it goes through a Polaroid filter or is polarized in some other way, like with reflection, that this occurs here. Now, this type of reflection that gives polarized light is the same reason that when we look at light that's polarized, then as I was saying before that interruption, this is why with reflected surfaces we have polarized light. And so at the beach or on the highways, Polaroid sunglasses are extremely helpful for cutting down on that reflected light that can be so blinding. Well, in the last section we had mentioned total internal reflection. And Snell's law tells us that the angle of total internal reflection has a sign that's equal to the ratio of n2 to n1. And that gives us the angle for total internal reflection, or what is sometimes called the critical angle. And we computed what that was in the last section, so I'm just reviewing that again, that Snell's law says that the sine of the critical angle is the ratio of the two indices of refraction. Light is dispersed because it turns out that different wavelengths have different critical angles and different indices of refraction. So, for example, if I take a prism like this and I shine light through here, it turns out that different wavelengths are broken up by different amounts, and therefore they come out at different angles. So if I put white light in over here, then in fact I get all the different colors out over here. This spectrum effect is such that the red is the least diverted. So red would be here and the violet would be up here. All of you are familiar with the different colors of the rainbow, and the rainbow will be seen in its normal order right here, where red is the least diverted, and it's diverted some. I should draw it that way better. And it goes red, orange, yellow, green, blue, and violet. Beyond the violet is the ultraviolet, and beyond the red is the infrared, meaning these are invisible to our naked eye, but this is the area of where we would feel heat. This is, of course, kills germs, our ultraviolet, and is captured by much of the ozone in the atmosphere. Otherwise, our planet would be rather deadly if it weren't for that ozone, and that's why we're concerned with ozone layers. Rainbows themselves come from the fact that sunlight enters and is internally reflected in water droplets. So we'll have a sun back here, and a person be standing here looking at moisture here in the sky, and you'll have a drop of water, and the sunlight will go into there and reflect back to the person. And as the light enters that droplet of water up in the sky and goes out, it's bent at two different angles. And therefore, when we look up here at these different droplets, we see at different angles in the sky, we see different colors arriving, because each one of these is going to send colors out at different angles. So the droplets that are up here will appear to be giving us a different angle. So what we see is a rainbow across the sky. That angle can be, that bouncing within the raindrops can occur more than one time, and therefore give us a double rainbow, and that's a rarer occurrence. And the second rainbow is usually less intense than the first one. So the critical things here are the Brewster's angle right here, and the second is Snell's law, which we had already discussed, and concerns the critical angle for total internal reflection within a material. One is the tangent, one is the sine.